Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the spectroscopy. And if you look at here, we are discussing as a chapter number 4. The name of that chapter is Introduction to Spectroscopy. An introduction to spectroscopy, and there we raise the question, what is a spectroscopy? And there we had defined spectroscopy, the interaction of electromagnetic radiation with matter is known as a spectroscopy. That is the simplest definition we have seen, and in the introductory part we have also learned there are two methods. One is a chemical method and another one is a physical method. How one method has greater advantages over the another method, that also we have seen. Generally, remember the application. Mainly why we are studying that spectroscopy, because these spectroscopies are the physical method, modern technique, and by using this technique we can easily find out the structure of the unknown organic compound. Once you know the structure, it is very easy to predict its physical properties as well as chemical properties. Another way, if you know the set of properties, from that also we can determine its structure, and once you know the structure, it's very easy to find out its physical properties as well as chemical properties. As we know that to find out the physical properties or the chemical properties by looking its structure, by observing the structure, but even today very powerful microscope available today, we cannot see the structure of that organic molecule by the naked eye, and therefore all these are the imaginary or the consequences to collect the information regarding the structure, and at the end we are finalizing the structure of that organic compound by using all these modern technique, and finally we are confirming it by synthesizing that molecule with known starting compounds. So that is the aim, that is the application of this spectroscopy, and various that electromagnetic radiation we are talking about, radiation and the light. And as we know that and today we are discussing the nature of the electromagnetic radiation. In the definition itself we mentioned that the interaction of electromagnetic radiation with matter is known as a spectroscopy, and therefore it is very essential to determine the nature of that electromagnetic radiation. Radiation exhibit dual nature. Radiation exhibit dual natures, particle and the waveform. Remember that radiation and the light, these are the two words generally we are referring here. Light and the radiation one and the same. When if you consider as a particle, then you can use a word light, and when you use the word radiation, we can consider the waveform, because the radiation exhibit the dual nature, particle and the wave function. And in studying spectroscopy, our emphasis is more on the waveform of the radiation. And if you observe, if you might have noticed, if there is a water, day-to-day life example, here I am giving. So the water in the lake, suppose there is a no blow of air, it is very calm. At that moment, that the water level is very silent, calm. If you throw one stone into it, there is a such type of the waves generated on that water level. So that is propagated. That waves are propagated in a particular direction, origin from where we are throwing that stone. In all direction that propagation of that waves are going. So this is one of the example of that wave. All radiation when propagate in wave form produce electrical field and magnetic field. Remember this word. All radiation when propagate in wave form produce electric field and the magnetic field. The direction of propagation and these two fields are mutually perpendicular each other, and that is shown in the figure. Let me show you the figure over here. This is one of the figure I am showing here. This you can remember, there are the three axes. So you remember this is the x-axis, this will be the y-axis, and this will be the z-axis. When we throw the stone on into lake, that waves are going like this. This generate this type of the waves, and another you can show like these waves, right? So this type of the waves, and remember this on z-axis there will be the electric field. This will be the electric field, generated electric field on z-axis. On y-axis there will be a magnetic field, and this is the direction of propagation. Suppose let us see here, this is the magnetic field I am showing with this dark. I am darkening this. This is the darken process, where you can remember this is nothing but as a magnetic field. This one magnetic field like this. So this is a magnetic field I am showing over here. Magnetic field, and so let me rub this also. Magnetic field we can show here. This is x-axis, so this is a magnetic field, and this you can denote by magnetic field. E is a electric field. Magnetic field, electric field, magnetic field, electric field, magnetic field, and the electric field. And here suppose these are, you can show like this. You can show these arrows here like this. In another way, you can show the arrows like this, their direction. Arrows are like this, or here again you can show this type of the arrows, like these arrows. Okay, this is the figure, direction of propagation of radiation. This figure indicate that direction of propagation, direction of propagation of radiation, direction of propagation of radiation. This is a figure represented here. Z axis represent the electric field, and y axis there will be a magnetic field, and x is the direction of the propagation. Remember here, this is a electric field represented by the symbol E. If x axis represent the direction of the propagation of radiation, this if x axis represent the direction of propagation of radiation, Z and Y axis represent the direction of electric field and magnetic field respectively. Electric field and magnetic field, Z and Y axis represent the direction of electric and magnetic field respective. Let us examine some of the parameter of the waves. Some of the parameters of waves, that is, first parameter is a wave length. Now wave parameter, and we are talking about here is a sum of the wave parameter. This indicates the direction of the propagation of the radiation, how it is wave propagated along the x-axis that we have seen right now. Let us see another the wave parameters. Now we are discussing about wave parameters, right? Wave parameters. Among that wave parameters, first parameter we are going to discuss. First one is a wavelength. First one is a wavelength. First one is a wavelength, and it is represented by symbol Y. This is a first parameter and very prominent parameter we are discussing here, that is a wavelength. What does it mean? One wave consists of one crest and one trough. For that, let me give one example over here. Suppose this is a x-axis, then we can draw this type of the wave functions. Let us see over here. We have shown here, this is a one wave. Now here I am representing symbol A, where this mountain is nothing but as a crest, and this one is known as trough, T-R-O-U-G-H, trough. And now the distance between two consecutive crests is nothing but the lambda max, or what we can call it, one end of the, this is direction of propagation. We can call it as a direction of propagation, direction of propagation over here. And now, or other way around, you can represent here the distance between this and this, we can represent by the symbol y. It means that wavelength is nothing but the distance between two consecutive crests or trough is known as wavelength. Remember, one wave consists of one crest and one trough. The crest and trough are alternatively spaced. Remember here, they are alternatively spaced. The distance between two consecutive crests or trough, or the distance between the starting point of the crest and end of the following trough, is called as wavelength of the radiation. So this is the first parameter we have learned over here. Second parameter will be amplitude. That is the second one, that is A, amplitude. And amplitude, it is represented by the symbol A. When one oscillation takes place, not this one, the maximum displacement of the wave from the x-axis is called as amplitude of the radiation. It is very simple. The maximum distance of the wave, the maximum distance, this is the maximum distance of the wave from the x-axis is known as a amplitude. So that is the simplest definition of the amplitude. The maximum distance of the wave from the x-axis is called as amplitude of the radiation. Now let us discuss the third wave parameter, which is the frequency, and that frequency is represented by the symbol mu, right? So this is the symbol represented for frequency. What does it means? How do we define the frequency? Let's see over here. When one oscillation takes place, one wave, that is one trough and one crest is produced. That is, during the oscillation, the wave travel a distance equal to its wavelength. It means that number of such waves length produced or number of oscillation completed per unit time is called the frequency of the radiation. remember here, number of waves, number of wavelength produced, or number of oscillation completed, number of oscillation completed per unit time is known as a frequency, is known as a frequency of the radiation. Remember once again, number of oscillation completed per unit time is called the frequency of the radiation. Let us see the next parameter, that is a parameter number 4th over here. What is that? Energy of radiation. Next one is a energy of radiation. Energy of radiation. Energy of radiation. This is the next parameter, and which is represented by capital E. Okay. Energy of the radiation is given by the equation. Energy of the radiation is given by the equation, and as we know that the equation according to as a Einstein's equation, E is equal to h nu. E is equal to h nu, that is E is equal to E is directly proportional to mu. Mu means frequency, just we have seen. E is equal to h nu. This is one of the equation you can remember over here. This is the equation number 1. E is equal to h nu, that is E is directly proportional to mu is a frequency, and where h is a Planck's constant, where h is a Planck's constant, and as we know that h is nothing but as a Planck constant, and mu is a frequency of radiation, and mu is a frequency of radiation. Mu is a frequency of radiation. Each and every term is very, very prominent or the significant while studying as a spectroscopy, and this type of the term you might have you may come across in while studying as an analytical chemistry, or even though in a physical chemistry. So however, we know that, and now let us see here, however, we know that here we are, however, we know that, however, we know that, what do you know? We know that we know that C is equal to mu lambda, right? Mu is equal to C is equal to mu lambda, and where C is a velocity of light, where C is a velocity of light, or here you can consider the velocity of radiation, right? Velocity of the radiation, when if you consider as a particle, then you can call it as a light. If you are studying as a wave, then you can always consider as a radiation. Radiation is nothing but as a light. Now, and therefore, if you rearrange this equation, what do you get? Mu is equal to C upon lambda. If that lambda goes from right hand side to left hand side, that goes into as a denominator. And now this equation you can call it as equation number 2nd, right? And substituting this in equation 1, what do you get? This equation number 1, if you substitute this, substituting in equation number 1, what do you get? substituting this in equation 1, substituting this in equation first, what do you get? We get equation number 1, we know that E is equal to H is a Planck constant, now is a C into 1 upon lambda. We can write this one, and this equation, as we know that here but C into H is a constant, right? C and H are the constant. H we know that Planck constant, C is the velocity of light, both are constant, and therefore what do you get? E equal to 1 upon lambda. This is again one of the important one that you can call it as a equation number 4, you can call it. Not this is equation number 1, equation number 2, this one is the equation number 3, you can call it. And this is the equation number 3, and this equation number 4, you can call it here. So, and this shows that energy of radiation is inversely proportional to its wavelength, and since energy is directly proportional to frequency, that is E equal to mu, but inversely proportional to wavelength, E is equal to 1 upon lambda, and frequency of the radiation and wavelength are inversely related to each other, and therefore we can represent, or we can say that E is directly proportional to nu, is inversely proportional to 1 upon lambda, and this is the equation we got here, and that equation number 5 we can call it. This is the equation number 5 over here. And now let us see as a wave number. 5th parameter we are studying, that is a wave number, right? Now we are talking about the 5th parameter, that is a wave number, and which is denoted by mu bar. So that is a symbol of wave number. Number of waves per unit length. Listen the definition carefully. Number of waves per unit length is called as wave number. Again remember, number of waves per unit length is called as wave number, and therefore mu bar is equal to 1 upon lambda. 1 upon lambda. This is the equation we got over here. Mu bar is equal to 1 upon lambda, and this is nothing but as the equation number 6, right? And now, and therefore from equation 5 it can be seen that, and therefore from equation 5 it can be seen that E equal to mu. That is the equation number 7, we can call it as here. So in this way we have learned whatever important parameters are required for the study of this spectroscopy with their equations So remember, equations are very simple. These are the parameter number 1 is the wavelength, it is represented by lambda. Amplitude, it is represented by A. Then frequency, it is represented by mu. Energy, which is represented by capital E. Then wave number, which is represented by mu. And these are the sum of the parameter we have learned over here. So in the next time we are going to discuss about the units of measurement for wave parameter. This is a point of discussion. Whatever parameter, wave parameter we have studied, what are its unit, that we are going to discuss in our next lecture. Let us wrap up the today's lecture today here. Thank you. Have a nice day.